Hi, my name is Ying Luo. The topic of our research project is Comparison of Collision Avoidance Strategies for Mounted Robots in a Warehouse. Here are the components of our research project, and let's start with the introduction. With the development of global e-commerce as well as the increasing demand for logistics systems and technologies, the development and application of logistics robots have gradually drawn attention on a worldwide scale. Traditional industrial intelligent manufacturers, as well as internet giants like Amazon, are gradually deploying logistics robots in their business process. According to the Global Industrial Robot Market Reports released by IFR in 2019, the global sales of industrial robots reached 424,000 units in 2018, and it is expected to maintain a growth rate of more than 12% in the next 3 years, as well as exceeding 500,000 units by 2020. With the gradual improvement of warehouse automation, Log Research Institute believes that mobile robot in warehouse will become one of the key infrastructures for automated or semi-automated warehouses. At the same time, the tasks faced by the robots have become more and more complex, and the environment has changed from single robots to multi-robots. Therefore, in recent years, the research on multi-robots collaborations in complex systems has received extensive attention from academia to industry. At present, the technology of intelligent warehouse systems is still in the development stage, which makes it necessary to reasonably solve the problems of task assignment in a dynamic environment, multi-robot pathfinding, coordination, and collision avoidance. Among them, pathfinding and coordination obstacle avoidance are especially important for the safe operation of the system and need to be highly valued. Basing on the known background, our research questioned about first, what collision avoidance strategy that can help effectively avoid the collision of multi-robots in the warehouse working environments, and second, how to enable the applied pathfinding method and collision avoiding executive rules to obtain a feasible path with fewer steps, as well as under what circumstances the collision avoidance strategies are feasible. By then, we identify 3 objectives. First, to identify collision avoiding strategies that can enable robots to work with no collision. Second, to conduct performance analysis and identify the collision avoiding strategies with the best performance. And third, to examine the scalability of collision avoiding strategies. Talking about the innovation of our research project, this research innovatively examined the collision avoidance strategies based on multi-robot pathfinding algorithm, cost-reducing purpose, the application in warehouses, and simulation experiments of rasterized maps. To the business in real life, our collision avoidance strategies can effectively improve the operational efficiency and economic benefits of warehousing. To the research in the future, our method increases the scalability and reflects the algorithm and strategy's effectiveness. In our experiments, a warehouse simulating program was written based on the following experimental assumptions. First, ignoring the actual size of the robots, every robot itself occupies 1 unit of nodes, and the speed of every moving robot is the same. Second, all robots can only move vertically or horizontally, and they can also move underneath the shelves. Third, the modified collision avoidance method are applicable in the 2D grids pathfinding process.
Hello, I'm Jialo. I will introduce the literature review into two aspects, pathfinding algorithms and collision avoidance strategies. Let's look at the basic pathfinding algorithm first. A good sample of the earliest pathfinding algorithm is steps first search algorithm. This algorithm begins from the starting node, calculates the cost of each node to the starting point, and ends when it reaches the target node. This kind of algorithm guarantees that the pathfinding is the shortest path, but the process is relevantly slow. In addition, the Dijkstra algorithm is an improvement of this algorithm. It sets different weights of each point in the map, which makes the type of algorithm more realistic. Another ancient algorithm as opposite to the Dijkstra algorithm is the best first search algorithm. The BFS algorithm evaluates the cost of other nodes to the target point rather than the starting point, which called heuristic function. Since the algorithm uses heuristic function to quickly direct to the target node, this method can calculate fewer points and find paths faster than the Dijkstra. However, the shortcoming is that the BFS algorithm may not find the shortest path. Is there any algorithm that can combine the advantage of above algorithms? The answer is A-star algorithm. The A-star algorithm is a very popular choice in pathfinding because its flexibility and can be used in various situations. Like Dijkstra, A-star can find the shortest path. Like BFS, A-star can guide itself with heuristic functions. Briefly explain the A-star algorithm. There are some standard terminologies. Function Gn represents the cost from the initial node to the arbitrary node n, and the function Hn represents the heuristic cost from the node n to the target node. When calculating from the initial node to the target node, A-star algorithm weights both functions. It calculates the function Fn, while Fn equals Gn plus Hn, and it compares the values of function Fn of all calculated nodes. After the main algorithm loop is performed, the best path is the node set with the smallest function values. And there are many A-star variants. Here are some samples. The first one is lifelong planning A-star, which is an incremental version of A-star. The difference between heuristic search and the incremental search is that heuristic search uses the function to achieve search the path, while an incremental search is to reuse the previous search result information to achieve an efficient search, greatly reducing the search scope and time. The second one is weighted A-star algorithm. To make the search direction better to the endpoint, based on the original A-star algorithm, an expansion coefficient epsilon, which is greater than 1, is introduced to weight Hn. So the weighted A-star algorithm can quickly search for the endpoint. Therefore, the weighted A-star algorithm is more resource saving and more time efficient, but the path may not be the best. The third one is dynamic A-star, which often called as D-star. Its main feature is to start the path search from the target position to the starting position. When there is a new obstacle in the path, the new obstacle will affect its path between the target position and the new obstacle. At this point, the computational overhead can be memorized by only adding nodes around the new obstacle to the open list for processing. Therefore, it's a dynamic pathfinding algorithm. While in the multi-robot warehouse transportation, another important issue is collision avoidance for the moving robot. It's difficult for A-star algorithm to make a particle in warehouse transportation without dynamic avoidance behaviors. Here are several samples of avoidance strategy. Firstly, the waiting strategy is the easiest way to avoid collisions. Specifically, when the next step is detected to collide, the lower priority robot stays in place until the higher priority robot passes the node. The advantage of this method is that it does not require CPU consumption. However, the shortcoming is obvious. This method can only avoid a side collision problem. If there are two robots face each other, a deadlock will occur. Secondly, replanning path strategy is the most commonly used strategy. To be specific, after detecting that a collision will occur as next step, the lower priority robot sets the collision point as an obstacle and recalculates a new path. Because the recalculation path involves many other facts, it can't solve all situations once and for all. For example, if a collision point is the destination, there will be no path to go. Finally, due to the rapid development of AI technology in the recent years, this approach came into the public side, and deep reinforcement learning is a method suitable for training robots to avoid collisions. AI technology is trained for future development. However, its strategy is a decentralized approach, which means that every robot calculates its own path and communication with each other. Things Decentralization is beyond the scope of our research project. This strategy is not adapted for implementation. Since our approach is mainly to compare the difference in avoidance strategy of path finding, I will divide the design into two parts: application design and experiment design. First, for preparation, a warehouse model is built that meets the following settings. Users can customize n times n size to a warehouse. And there are four shelves on the left side of the warehouse. Also, there is a large assemble desk which occupies four nodes at the right of the warehouse. In order to simulate the collision situation of multiple robots in the warehouse, up to 6 robots are added to work at the same time, and the robot's standby point is at the bottom of the map. And the work principle of the robot is to receive the task, go to the specific shelf to fetch the goods, and then send it to the assemble desk. When the task is completed, the robot checks the task list, return to the robot's standby point if there is no task, or continue performance other ones if there are still tasks. All the paths found is use the A-star algorithm. After the preparation of the warehouse model is completed, we explore the wait-only collision avoidance strategy and design a suitable wait-only strategy to ensure that the task can be completed by robots without collision. Although previous literature reviews has shown that the waiting strategy cannot be achieved independently. Through our group discussions, we have found that a collision-free pathfinding model can be built in a brute force form, which is illustrated in detail during implementation. Although the wait-only collision avoidance strategy can be implemented, there are still many shortcomings. On this basis, our team continued to design collision avoidance model with recalculation, which involves other luxury collision avoidance strategy in special cases, such as stepping back or waiting. These details are addressed in implementation stage, so the target is to present a sophisticated recalculation collision-free pathfinding model with better performance. After coding the program, we conduct a simulation experiment on these collision avoidance models in 3 ways. First, test the collision avoidance implementation and making sure that there are no collisions happening in normal situation. Second, collecting data such as the number of collisions, the total number of steps, and the recalculation time to further analyze the pros and the cons of these strategies. 3. Testing the scalability of our strategy and find a way to improve our implementation in the future. In general, we try to prove that our strategy are valid in normal circumstances and find out the limitation of our strategies.
Okay, sorry. In the following sections, I will be introducing the details of our implementation as well as a short demonstration of our program. And then we will analyze the performance of our strategies and so that we can prove we have achieved our research goals. Before moving on, we want to give a definition of what collision is in terms of code. So there are two cases of collision. We call the first one arriving at the same grid at the same step. It is reflected in code as, for example, at step I, robot 1 next step at step I equals robot 2's next step at step I. The second case is swap position. As you can see here, the two robots' next step is equals to another robot's current step. In this case, this is also a collision. And also, here's a short description of the A-star algorithm implementation. So we use a standard A-star implementation, which is based on priority queue. So in this while loop, each time we try to find a next node with a better distance. Also, we define our heuristic function as the Euclidean distance between two squares. Here's the data type for our robot. It has some properties and a few methods to help us calculate its next move. And then here's the basic method flow of our program. So the main body of our program is a while loop, with the terminating condition being all robots finished tasks and the task list is empty. So in each iteration, we will loop through the robot collection to determine each robot's next step, and then we update this variable map to keep track of collision status. And then after each robot has made its move, we will see if it has finished its current path. If finished, we will assign a new task if the task list is not empty. Otherwise, it will return to its original position. Okay, here's the naive approach we have come up with at the first place. It's actually just an extra line of code. Here, before we determine a robot's next move, we say if its next move is occupied or not. If it is occupied, if only when it is not occupied, then the following code will be executed, which means if the next step is occupied, this robot will simply wait at its current position. However, this approach will not work at all because, as the charts show here, if there are a collision, if there a wait happens, both of the robots will wait forever, resulting in what we call earlier a deadlock. And then, if two robots has entered a deadlock status, all robots will eventually enter deadlock. So this approach simply does not work. Then we have to work around. We have to think about how to work around deadlocks. We have come up with two strategies to do that. The first one being avoid deadlocks in the first place. This is our brute force approach. The second one is when deadlock happens, we want to do something to address this. This is called optimal approach. So brute force approach is also called pre-calculated weighting. The core idea of this approach is like this. Instead of giving tasks to all robots under no condition, each time when we give a task, we decide if this task has conflicts with all previous paths. So you can see from this section here, each time we get a task from the task list, then we determine based on this function if this path has collision with previous paths. If it has collision with previous paths, this task will not be assigned to this robot. Once all available task is assigned, this program will enter what we call a moving phase. So during moving phase, each robot will, just like the basic program flow, they will move their next step until all robots has finished their tasks and return to its original position. Then we will begin another round of task assignment phase. So at the end, all tasks will be finished and all robots will be back to its original place. Here's a typical running instance of this approach. One thing to be noticed is that in most cases, only a few robots will move. This is because the following robots will have paths if they carry out their tasks. Next, I will be introducing the optimal approach. It is actually quite like the basic program flow. The only difference is that instead of waiting, we simply recalculate a new path with the collision spot as an obstacle. However, we will also do a check on this new path. If the path is null, or you can say if the path is empty, this robot will decide whether to wait or take a step back. Because if we bluntly make this robot take a step back, it will run into another collision. There's a possibility for that situation. So we will also do another collision check. If no collision, this robot will safely step back, otherwise it will wait. Also, if the new path is available, the new path will replace the robot's old path. So in this situation, we can safely avoid all deadlocks and all collisions. Here's an instance for the optimal approach. Unlike the brute force approach, all 6 robots will be carrying out tasks. Okay, here I will show you a short demo of our program. Our program is mainly consists of 2 classes. The first one being grid class. So this class does practically everything, including drawing the grids and also make the robots move. And the fetch class will help us get the paths using A-star algorithm. As you can see here, we have several A-star algorithms already. So once we start the program, we have several options. And by clicking each option, we can make the robots run with the corresponding option. So brute force is obviously taking much more extra steps. And the optimal approach is much faster. Also, the wait-only strategy will enter a deadlock. Okay, at last, I will give an analysis of the performance of our strategies. So the first point we want to prove, and it is also the basis for our program, is that we can safely say both of our strategy will not hit collision, as you can see from this table. Also, we observe that the optimal approach takes only a few extra steps, while the brute force approach takes much more extra steps. However, this difference is is decreased under a larger square. We define R as the ratio of the number of robots to the number of squares. We can observe from these two data charts that as R drops, optimal approach will have close performance to the no avoidance strategy. And also the brute force strategy's performance is significantly better. It takes 2 times extra step to only 60% of extra step. Also, another interesting finding is that in optimal approach, not all robots take much more steps. You can see here robot 6 takes even less steps. This is because the order of tasks has been altered in optimal approach. So we want to say that the order of tasks actually matters. At last, we want to identify the scalability of our optimal approach. We have run another experiment. As you can see from the chart here, when R is 0.6, the time spent on recalculation is 10 times of when R is 0.3, as you can see here. Also, in this situation, deadlocks will occur. This is caused by limited squares and the fixed shelf and assemble desks numbers. So in this case, our strategy will not work at all. So according to our calculation, we can say that the upper bound for our approach is 0.5.
In conclusion, first we understood the pathfinding algorithm of multi-robots in the warehouse, as well as the strategy of avoiding collisions through our literature review. Second, we conducted our own research method as well as the experimental procedures and make our efforts to implement them. Then we built a program for simulating the warehouse. We wrote a Java code of the pathfinding functions of the robots based on A-star algorithm, applying the collision avoidance strategies we decided to use, and debug them until no error or collision occur. Through the experimental data, our method has been proven to ensure that the robots can avoid other robots that appear on their paths in the warehouse transportation under assumed conditions. Brute force's method is more suitable for fewer robots in a warehouse. The method avoids the CPU usage required for recalculating paths. It should be emphasized that the optimal strategy is a better solution than the A-star algorithm in the dynamic environment. Yet, there is still an upper limit. When the number of robots is greater than half the size of a warehouse, there is a possibility of deadlock. However, this situation rarely occurs. Under normal circumstances, the reliability of the collision avoidance strategy is still trustworthy. Here is our reference list, and thank you for listening.